In this video, we are going to review moles, molar mass, and how we can use that to do different stoichiometry problems. So the mole is the unit of measure for an amount of a chemical substance, and it's very similar to how we might say a dozen is 12. So a dozen donuts is 12 donuts. A mole is simply 6.02 times 10 to the 23rd particles, and I will quite often say 6.022. That's just one additional significant figure. But 1 mole is equal to 6.022 times 10 to the 23 things, and they can be atoms or particles, molecules, grains of sand, any of those things. It's 6.022 times 10 to the 23 of them. And we call this number Avogadro's number. Now we can use this mole relationship to convert between the number of particles and the mass of a substance, as we're going to demonstrate in this video. Now, the atomic mass of any substance expressed in grams is called the molar mass, and it always has units of grams per mole. AMU, atomic mass units, is very, very similar. It's essentially the same thing. And we get these numbers, so 12.01 for carbon, we pull that directly off of the periodic table. So on the periodic table, the decimal number that you see underneath each element is the atomic mass for that element. So carbon on ptable.com, it says 12.011, and that is grams per 1 mole. Nitrogen, it says 14.007, and again, the units is grams per mole. It's basically saying that that's how much 1 mole would weigh. So if you had 1 mole of carbon, it would weigh 12.01 grams if you were to put it on a scale. Nitrogen, so the periodic table says 14.01, but remember nitrogen is one of those diatomic elements. So the molar mass of diatomic nitrogen gas is actually 14 times 2, so that's why we have 28.02 grams per mole. So if you had 1 mole of nitrogen gas, it would weigh 28 grams. Now, to calculate the molar mass of a compound, you simply sum up or add the molar masses of each element, and you have to make sure to take into account if the element has multiple atoms in it. So for example, this nitrite, we have copper 2 nitrite here. This is your copper, and this NO2 is the nitrite polyatomic ion. It's an NO2, so 1 nitrogen and 2 oxygens. And then there's also another 2 out here saying we have 2 copies of the nitrite polyatomic ion. So now all they're doing here is just adding up all of the atomic masses from the periodic table. So the 63.55, that is the atomic mass for copper. And then 14.01, 16, and 16 is for nitrogen, oxygen, and oxygen respectively. And then this 2 is referring to this 2 out here. So this 2 is essentially doubling everything we calculate on the inside. And then if we do that calculation correctly, so if you were to try to do this on your calculator or independently as practice, try to find the molar mass of copper 2 nitrite, you should get about 155.57. And the units are always grams per mole. So 155.57 grams per 1 mole. So now we can use this molar mass to convert between grams and moles for a particular substance. And we have this equivalence where we can say 6.022 times 10 to the 23 particles equals 1 mole, and 1 mole equals the molar mass. So if we want to convert from particles to mass, or from grams to moles or moles to grams, we're going to use either Avogadro's number or the molar mass, and we're going to do a few examples. Another molar quantity, if you will, is called the molar volume. So for a gas, at standard temperature and pressure, and that's very important, 1 mole of gas is equal to 22.4 liters, and this is called the molar volume. Now it has to be at standard temperature and pressure, STP, which is defined as 1 atmosphere of pressure and 0 degrees Celsius. So 0 degrees Celsius is the freezing point of water, so pretty cold. Notice that it is not room temperature. Room temperature is about 22 to 25 degrees Celsius. 1 atmosphere pressure is the pressure you would feel around sea level. But it has to be at STP, standard temperature and pressure, for this thing to be equivalent, where it's 1 mole equals 22.4 liters for a gas. And also this obviously only applies to gases, not solids and liquids. So for all of these in the table, we're saying, we have 1 mole, which means we have 6.022 times 10 to the 23 particles, which all of these for gases would also be 22.4 liters. But notice what's actually different for all of these is the molar mass. And the molar mass is different because all of these are different. These are different compounds. So for hydrogen on the periodic table, it says on ptable.com 1.008 grams per mole. And then hydrogen is one of those 7 diatomics that you need to make sure you memorize. So 1.008 from ptable.com multiplied by 2 gives you the 2.02 that they have here. Same thing for oxygen at 16 on the periodic table, multiplied by 2 because it's diatomic, we get 32, and so on. All of these are just conversions, so 1 mole equals 6.022, 1 mole also equals 22.4, and 1 mole can also equal the molar mass depending on the identity of the substance. We can also calculate the density of a gas. So keep in mind that gases are much less dense than liquids. So for example, if you were to have, let's say like a soda, and you open the soda can, or it's a bottle where you can actually see through it, and when you open it, the bubbles that are inside of your soda, they rise to the top. They do that because they're much less dense. So gases are much less dense than liquids, which is why the gas bubbles in your soda will float to the top. Now we can calculate the density of any gas at standard temperature and pressure using what we've learned. So the molar mass of the gas over the molar volume. So molar mass, remember, is grams per mole, and molar volume is liters per mole. So just looking at the units, moles would cancel, and that gives us units of grams per liter. Now recall that density in general is a mass over a volume. So for other substances like water, we might normally provide the density in units of grams per milliliter. It's still a mass over a volume. So same thing with gases, it's just going to be grams over liters instead of grams over milliliters. But this is one way that you can calculate the density for any gas, provided you know the identity of it, and it's at standard temperature and pressure. You can calculate the density of the gas at standard temperature and pressure. So just a quick example, so we've got CH4, which is called methane. If we're going to have to calculate the density of this gas, we first have to know the molar mass, so that's what they did right here. The 12.01 is for the carbon, the 1.01 is for the hydrogen, and then we have a 4 out front because there's a 4 in the formula. There's 4 hydrogen atoms for every single CH4 molecule, and we get a molar mass of 16.05 grams per mole. The molar volume of methane at standard temperature and pressure is 22.4. So we divide those two numbers, and like I mentioned earlier, moles will cancel and we'll end up with units of grams per liter. And we get 0.717 grams per liter. And I encourage you to do this on your own calculator just to verify that you can replicate the result. You can get the same answer. We can also use molar volume to calculate the molar mass. So it's kind of like working backwards a little bit. So an unknown gas has a mass of 4.29 grams, and we discover it occupies a volume of 1.50 liters at standard temperature and pressure. So we don't have a mole, or we don't necessarily have a mole. We have 4.29 grams of it, and we have to figure out what the molar mass is. So setting up our units, if we do grams over liters, that's kind of like we're calculating the density here. And then we can use the molar volume to turn the liters part of this into moles because we want to get molar mass. Molar mass always has units of grams per mole. So they put the 22.4 liters on the top here and the 1 mole on the bottom so that the liters would cancel out. And then we're left with units of grams per mole, which is the units of molar mass. So we've got three different interpretations for the mole. We've got 1 mole equals 6.022 times 10 to the 23rd particles. 1 mole equals the molar mass of the gas or the substance, whatever it happens to be, based off of the decimal values from the periodic table. And 1 mole equals 22.4 liters for a gas at standard temperature and pressure. So 3 different unit factors for the sake of doing conversions to go between moles, particles, grams for mass, liters for volume, and back and forth. So here's an example, calculating or using molar volume to calculate moles. So a sample of methane occupies 4.50 liters at standard temperature and pressure. How many moles of methane are present? So we're going to start with what we were given, 4.50 liters of the CH4 methane gas. And then here they're using the molar volume to cancel the liters and give us moles. And then again, with all of these, I encourage you to try to do them on your calculator just to make sure you can successfully calculate the same thing that we got on the slides. So now calculating mass from volume, this one says what is the mass of 3.36 liters of ozone gas. So ozone exists in the upper atmosphere and it generally protects us from UV light. And standard temperature and pressure again, which is required if we're going to be using the 22.4 liters per mole conversion. So we want mass, which means we want to calculate grams. We were given liters, so we start with what we were given. This first conversion is to change liters into moles. So we put the 22.4 liters on the bottom so that the liters cancels. And then with the second conversion, we're using the molar mass of ozone. Now ozone is O3, so you need to do 16 times 3, and you get about 48 grams per mole to get the molar mass of ozone. And then we put the 48 on the top right here so that the moles can cancel. They should not have put this little green line right there. They should have put the green line on the bottom to show that moles is canceling. And then we get units of grams and double check that you can get the same answer. Hopefully this answer is correct. So sometimes these slides have typos on them. So another one, how many molecules of argon gas are in a sample that occupies 0.430 liters at standard temperature and pressure? So we want molecules, and we're starting off with liters. So we start off with what was given, the 0.430 liters. To convert liters into moles, they put the 22.4 on the bottom so that liters cancels. And then this is Avogadro's number. So recall Avogadro's number gives you a conversion to go between moles and molecules. Or it could be between moles and atoms. We could also write, in fact we should write atoms right here, because argon, a noble gas, exists as atoms, not as molecules. But the principle is the same. We would be multiplying by Avogadro's number so that the moles cancels, and we end up getting this number. And again, practice. Make sure you can get the same number on your calculator, especially when we're dealing with exponents like this. So scientific notation, it can be tricky to get this, problems like this put in your scientific calculator correctly unless you practice. So then percent composition. Percent composition of a compound is basically listing the mass percent of each element in that compound. So it's telling you how much of a sample of water is hydrogen and how much of it is oxygen by weight. So all water, whether it's a drop of water or a cup of water, is going to be 11% hydrogen by weight and 89% oxygen by weight. So that's what they mean by mass, pretty much by weight, same thing. So there's a couple steps anytime you're doing a percent composition problem. The first thing is more like a hint. It basically says just assume that you have 1 mole of the compound, because if you assume that you have 1 mole of the compound, you can then calculate how many grams of each element you have in that compound. So if we had 1 mole of water, that means we would have 2 moles of hydrogen atoms and 1 mole of oxygen atoms, because for every 1 mole of water, there's 2 moles of hydrogen and 1 of oxygen. For every molecule of water, for every water molecule, you have 2 hydrogen atoms and 1 oxygen atom. So then what we're doing here is just calculating the molar mass of water. So we have 2 hydrogens and 1 oxygen. We get about 18. This is 18 grams per mole. Then to find the percent composition, it's basically the part over the whole. So the part of water that is hydrogen divided by the whole thing. And then the part of water that's oxygen divided by the whole thing. So the hydrogen part was about 2.02, so we got that on the previous slide. And then the part that was oxygen was about 16. So here they have 2 over 18 and 16 over 18, and that's where we got the 11 and the 89% values that you saw on the previous slide. And then with both of these, of course, we are multiplying by 100% in order to turn the decimal into a percent. So here's another example. So TNT, trinitrotoluene, it's a white crystalline substance that is pretty explosive. Calculate the percent composition of TNT. Now you'll have to pay attention to the formula. So we've got 7 carbons, 5 hydrogens, and then this 3 out here is basically telling us we have 3 nitrogens and 6 oxygens total for every single molecule of TNT. So then they calculate the molar mass, we get 227, but let's take a look at how they did that. So 12.01 is the atomic mass for carbon right from the periodic table. And then we have 7 here because there's a 7 in the formula. 1.01 for hydrogen because that's from the periodic table, and a 5 right here because there's a 5 in the formula. And then the 14 is for nitrogen, and the 32 is for the 2 oxygens, and then we have a 3 out front because of this 3 right here. And then just kind of explicitly writing out the numbers because we're going to need them on the next slide. 84 for carbon, 5 for hydrogen, 42 for nitrogen, and 96 for oxygen. You add it all up and you get your 227.15 grams per mole for the molar mass of TNT. Now we're going to use this 227 to do the percent composition part of it. So again, it's the part over the whole. So the part of TNT that's carbon divided by the whole thing, the part that's hydrogen divided by the whole thing, the part that's nitrogen, and then the part that's oxygen. So notice here in the 227, this is the molar mass of our TNT. And then we've got 84, 5, 42, and 96 for carbon, hydrogen, nitrogen, and oxygen. So the same numbers that we had over here when we were adding up the molar mass. And then, of course, multiply by 100 in order to make it a percentage. So then mole ratios. So anytime you have a chemical equation like this one, you can translate this into a sentence that basically says something along the lines of 2 moles of nitrogen monoxide gas react with 1 mole of oxygen gas to yield 2 moles of nitrogen dioxide gas. Or we could say 2 molecules of NO plus 1 molecule of O2 makes 2 molecules of NO2. The important thing is the numbers, so the 2 and then the 1 and then the 2. Now keep in mind that anytime we balance chemical equations, if the coefficient for balancing is a 1, we usually don't write it in. But the mole ratio is basically what these coefficients are. So the fact that 2 react here with 1 here to produce 2 over here, that's what we're calling the mole ratio. So the coefficients indicate the ratio of moles of reactants and products in terms of how the reactants react with each other and how much product you get for the reactants, etc. And this mole ratio is very useful in the sense that we can use it to convert from moles of one thing to moles of another. So we're going to use this with several different types of stoichiometry problems. So just to go through them each, we have a mass to mass, so that's like converting from grams of one thing to grams of another. We could also go from grams to liters, or we could go from liters to liters. Now, we're going to do the grams to grams one first, but we can't just simply go directly from grams of one to grams of the other. We have to convert to moles first. So there's 3 steps in these mass to mass stoichiometry problems. The first step is to convert the given mass, which is probably in grams, to moles using the molar mass of that substance. So if we wanted to go from grams of A to grams of substance B, we would first have to convert to moles of A and then convert to moles of B to go to grams of B. So this first step, we would use the molar mass of A, whatever that is. And doing moles of B to grams of B, we would again use the molar mass to convert from moles to grams. This middle step is going to use the mole ratio. So if we had the balanced chemical reaction of A reacting with B, whatever the coefficients are, help us go from moles of A to moles of B. And we'll do an example. So that was that second step that they were talking here. And then the third step, we're basically using the molar mass of the second substance to go back to grams. Mass volume is very similar. So the first step is essentially the same, and even the second step is the same. So step one, going from grams to moles using the molar mass. Step two, we're using the mole ratio, so the coefficients in the balanced chemical equation. And then number three, instead of converting to grams of the other substance, we're going to convert to liters using the molar volume. And if it is at standard temperature and pressure, that means it's 1 mole equals 22.4 liters. So here's an example. It says how many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum with dilute hydrochloric acid. So we've got a balanced chemical equation already, which is great. We're going to need to figure out the mole ratio between aluminum and hydrochloric acid. So here's aluminum in the balanced chemical equation. Here is, oh, and actually my mistake, we need to go from aluminum to hydrogen because it says how many liters of hydrogen. So we're actually going from aluminum over here to hydrogen where it is a 2 to 3 molar ratio. So the first thing, convert grams to moles, and we can just use the molar mass. So directly off the periodic table, 26.98 grams per mole. Then go from moles of aluminum to moles of H2 using the balanced chemical equation. So the molar ratio is the 2 to 3 molar ratio. And then since hydrogen is a gas, we can convert hydrogen gas from liters to, or sorry, go from moles to liters using the molar volume. So that's the 22.4 liters per mole. So this was the game plan that we just outlined, grams to moles to moles to liters. This is our setup. So we start with what we know, which was 0.165 grams of aluminum. This is the molar mass of aluminum. So the 26.98 came directly off the periodic table. We put the 26.98 in the denominator so that grams of aluminum cancels. Next over here you have your molar ratio. So in the balanced chemical equation we've got a 2 for aluminum and a 3 for hydrogen. We put the 2 on the bottom because the 2 was associated with aluminum and we want moles of aluminum to cancel. The 3 was associated with the hydrogen, so that goes on the top. And then lastly, we use the molar volume of 22.4 liters per 1 mole of hydrogen. And we put the 22.4 on the top so that the moles of hydrogen can go on the bottom so the units can cancel. And then we should get 0.205 liters of H2 if we did that correctly. So another example, going from volume, so 9.21 liters, to mass, so they say how many grams of sodium chloride are needed to produce 9.21 liters of oxygen. So taking a look at the balanced chemical equation, here's our oxygen with a 3 in front, and sodium chloride is this thing, NaClO3, and it's a 3:2 ratio, similar to the last problem. So the first thing, we're going to start with what we know, 9.21 liters. Next, we can convert to moles using the molar ratio because the O2 is a gas. And we put the 22.4 on the bottom so that the liters cancels. Next, we're using the molar ratio. So it's a 2 to 3 ratio from the sodium chlorate to the oxygen. And we put the 3 on the bottom because that was associated with moles of oxygen and we can cancel our units. And then this last one, since the sodium chlorate was a solid, and we're going, they said how many grams, we're going to use the molar mass. And we put the 106.44, which is the molar mass of the sodium chlorate. We put that on top so that the 1 mole can go on the bottom so that moles of sodium chlorate can cancel. And we should get 29.2 grams of sodium chlorate. So the last one is volume to volume problems. And this one kind of has a shortcut to it because of this thing called the law of combining volumes. And it's actually very similar to law of conservation of mass. Essentially, if you have certain volume of gases on the reactant side, you should end up with the same volume of those gases on the product side, provided everything's at standard temperature and pressure. So with this example, they're saying 10 milliliters of hydrogen gas react with 10 milliliters of chlorine gas to produce 20 milliliters of HCl gas. So if we were trying to illustrate law of conservation of mass, it might say like 2 liters here and 10 liters here makes, 2 grams, 10 grams makes 12 grams. But law of combining volumes is in principle very, very similar to law of conservation of mass. Whatever you start with in terms of mass, or volume in this case, you have to end with. And then our molar ratio, if we needed that, it says 1 to 1 to 2. So that means we have a 1 in front of hydrogen, a 1 in front of chlorine, and a 2 over here for HCl in the balanced chemical equation. So here's just kind of like another illustration of what we mean by the law of combining volumes. So if we had 1 volume of hydrogen reacted with 1 volume of chlorine, we would produce 2 volumes of our product, the HCl gas. Now, volume to volume problems, because of the 22.4 liters per 1 mole for any gas at standard temperature and pressure, we can kind of take a shortcut. So it breaks down to just one step. It really is 3 steps, but step 1 and step 3 kind of cancel each other out. But essentially, we can just convert the given volume to the unknown volume using the mole ratio. So basically, what the coefficients are from the balanced chemical equation. So here's an example that says how many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas. So they're asking about liters of oxygen, and we're starting off with 37.5 liters of SO2. So, and then paying close attention to the molar ratio, that's what they're doing here. From the balanced equation, 1 mole of oxygen reacts with 2 moles of sulfur dioxide, so they react in a 1 to 2 ratio. Here's our balanced chemical equation, and this is just reminding us what we were trying to do. Go from liters, the 37.5 liters of sulfur dioxide, to liters of oxygen. So we start off with what we were given, 37.5 liters of SO2. We just noticed that it's a 1 to 2 ratio, and we put the 2 on the bottom so that liters of SO2 cancels. And that gives us 18.8 liters. Again, just one step. Technically, because this in the middle is a mole ratio, to go from moles of one thing to moles of another, we should, but we don't have to, convert from liters to moles, and then to moles, and then to liters. So this would be, for example, liters of SO2 to moles of SO2 to moles of O2 to liters of O2. But for this first and third conversion, you're going to end up using the 22.4 liters. So for the first one, you'd end up dividing by 22.4, and then in the next one, you'd end up multiplying by 22.4, so they kind of cancel out. And that's why a volume-to-volume stoichiometry problem can break down to just a single step instead of multiple steps. And then in this one, just like as extra practice, they ask how many liters of SO3 get produced. So again, starting with what we know, 37.5 liters of SO2. This is the mole ratio between SO2 and SO3 when we end up getting the same value. So 37.5 liters of SO3 if we start with 37.5 liters of SO2.